Welcome to Crash Concepts, where the economy, energy, and the environment are explored. Up next, fresh ideas and insights into the factors that are driving the world and shaping your future. Presenting information you can't afford to live without, here's Chris Martinson.
Hello, this is Chris Martinson here, and I'm in beautiful Charleston, South Carolina. And I have the opportunity and the pleasure to speak with Willett Kempton today. And we're going to be talking about energy, and we're going to be talking about in particular, electric energy and how this might play a role in the coming energy scenario that we're looking at over the next few years. So, Willett, welcome to the program, and thank you very much for being here.
Thanks, Chris.
And can you tell, for the listeners who may not know who you are, tell us something about yourself and your qualifications and how you came to be interested in this subject, if you will.
Okay. I'm a professor at the University of Delaware. I'm in the College of Earth, Ocean, and Environment, so that gets at the environmental part and the wind and water power, and I'm also a professor in electrical engineering. I direct a center called the Center for Carbon-Free Power Integration, so we're trying to figure out how we get these fluctuating energy resources into a form that's usable to humanity.
Fluctuating meaning because alternative energies like wind and solar fluctuate? Is that what?
Exactly.
Okay. And this has been a big problem, as I understand it, because storage is still one of the key weaknesses in the whole electricity story. Is that
I would agree
accurate?
with all of that, except it has been, because the electric system is designed to deal with fluctuating load. That is, you turn on your electroplater in the morning and all of a sudden the power sector has to come up with a megawatt in a few seconds. So they're set up to do that. But once you get over a certain level, maybe 20% is kind of a mythological number, but it's somewhere around there. Then you start having to have special systems to deal with large amounts of wind and solar.
Special systems, but still storage is an issue. So if the wind doesn't blow, for instance, and we were trying to use wind as our base load, we would discover that we didn't have any base load at that point. Is that right?
Right, yeah. So, right now we have more generation than we need. So it's just a matter of ramping something up or down. But as the system evolves, we will sometimes have too much electricity and other times not enough. It's both problems. And the nice thing about storage is when you've got too much, you store. When you don't have enough, you release from storage. So storage is one way of doing it. There's other ways too, like you have long-distance transmission. So when the wind's blowing one place, it's not blowing another. Mm-hmm. It tends to balance out pretty nicely, actually, if you have the correct areas connected.
Right. So what are our storage options today, and what might be coming down the pike?
Well, the U.S. Power sector has about 2% of its capacity is storage, and that's almost exclusively what's called pumped hydro. So it takes water in a lower reservoir, pumps it uphill when there's excess electricity to a higher reservoir, say a reservoir that's been built up on a hilltop or whatever. And then when there's not enough electricity, it lets it flow back downhill. So you get about 70% back out. You lose 30%. But it's worth that loss in order to get the electricity exactly when you need it. Mm-hmm. The other options for the future, of course, everybody thinks batteries. Batteries are relatively expensive, but very fast response. There is using compressed air energy storage, it's called. So you pump down into a geological formation underground, you compress air, and then you later release it through a turbine. You could burn natural gas as you're doing it, which expands it much more, or you can just run it out through a turbine. So those are the sort of primary storage methods. The flywheels, gets into the more esoteric stuff. And within batteries, there's a wide variety of electrochemistries and configurations.
I've heard a little bit about capacitors, too. I don't know, is that just pie-in-the-sky drawing board, or is that a realistic?
Well, a capacitor is very small amount of energy and a high amount of power. So it might be used in a hybrid automobile, for example, to get a sudden burst for acceleration that would last a couple of seconds. But it's not really useful for utility storage because you can't store very much energy that way.
Mm-hmm. Okay, so, but as we look forward into this landscape, how important is solving storage to getting to, say a much more sustainable or in some way an electrical situation where we're able to use a lot less fossil fuels and able to use more alternatives. Is this a big area of inquiry that we're going to have to solve, a medium, low?
I'd say big. Like I said, there's other ways to deal with fluctuations, but none are perfect. For example, that long-distance transmission I mentioned is one. Another is finding renewables that don't have fluctuations, like the Gulf Stream is big. The Gulf Stream can run approximately the base load demands of the Deep South in the United States. And it's 365, constant power plus or minus 10%.
So there we would anchor some sort of in-water turbines or
Right.
something, and,
Right.
and they would just be in the middle of a ocean river, and
Yeah,
somehow we'd
right.
be able to connect that back into the grid.
Yeah, it's not that hard. You just run your transmission. You run your power lines back. And there's 4 companies working on this right now. Technology is plausible. Costs look to be very low. So it's a finite resource. Though you can run the Deep South, which is great,
Yep.
because they don't have other renewables really, except PV, which is very expensive, photovoltaics. So that's one where you don't need storage. You just need to figure out the right resource. Another one like that is high altitude winds. It's 20 years out probably, but there's 50 million or so being invested right now in development of high altitude winds. Those are also very steady and large. It's 100 times the energy demands of mankind is in the high altitude winds. High altitude is 20, 30 kilometers, kind of altitude you fly in when you're in a plane. But generally with the stuff we've got today, which is surface winds and photovoltaic, you're going to need some kind of storage to get beyond 20 or 30% of the system. We're at 2% now. It's not like we need it tomorrow or next year, but we need to start working on it now.
Right. So as we look forward, tell us about how much of a role right now does wind and solar play? So if we said 100% of the electrical use right now, how much
About
of that
1%.
1%. And most of that's coming from wind at this point, I would assume?
Yes, right.
So the bulk. So have you been involved in any projects that would be significantly adding to that? I'm trying to get an understanding here of the scale of these projects, what's involved, where the money comes from, how long they take, just really some of the actual issues involved in going from an idea, I like the idea of the Gulf Stream, to actually being able to flick the switch and we're supplying the Deep South.
Wow, that's a great question. I haven't been asked that before, but I have a great answer to it, actually 2 answers. So I'll give you 2 cases. One is, let me give you 3. One is you want to put a solar system on your home. You call a contractor. This is a mature business, highly subsidized. So you call a contractor, they come out, look at your home, give you a bid. You write a check for $20,000 or something, and you get a bunch of solar panels put on your roof. And, during the middle of the day, you spin your meter backwards pretty fast. And other times of the day, you're drawing, and the net is what you pay, or the utility pays you. And depending on the state, and all that. So that's pretty well established, and that's like a 2 or 3 month period. And it's totally just commercialized business. Second example is our college campus in Lewis, Delaware. The College of Earth, Ocean, and Environment of the University of Delaware. We looked at the winds there and we said, gee, this is a pretty windy site. We're right on the coast here. We've got the sea breeze, which comes in and out during the day, plus storms, nor'easters, So is this something that would make sense to have a wind turbine? So we put up a meteorological tower. That's a $100,000 investment or something to do a study, put up the tower and all that. After a year, we did the analysis. Hey, this could pay for itself. So that was a year to do the study, and then a second year to actually get to a built machine that's generating electricity, which is really quite fast. And it was a little rough getting it all out the door in time, but we were facing a situation where the vendor of the turbine, Gamesa, said, if you can get this out while we're in a lull, we can give you a lot more favorable terms and get it out now, as opposed to you wait until the 100 turbine wind farms getting built and we realize we can't put one of them in because it's conflicts with something, then you'll get it. So we pushed that very fast and did the whole thing in a year. And now it's a 2 megawatt turbine, it runs that entire campus. That's 2 large laboratory buildings with offices, wet marine labs pumping water, entire ship operations port, basically. It's 2 ships that are out there, 2 ocean-going ships, a conference center. That's all run off this single 2-megawatt utility-scale wind turbine. And that was 2 years, to answer your question. Mm-hmm. And the economics are basically we pay $6 million up front and we get $600,000 in electricity per year, plus should be another $100,000 in renewable energy certificates and so forth. So it's not a 2-year payback, but it's perfectly reasonable. It's the kind of thing a university invests in. Because you look at a university, there's slate roofs and stuff. They're looking at a 50-year kind of time horizon. And the third example is Blue Water Wind, which is an offshore wind farm. They originally proposed it for 600 megawatts. It got downsized in the regulatory proceedings. But at 600 megawatts, it would produce about 17% of the electricity of the state of Delaware. It would have a noticeable impact on the health impact of power generation in Delaware. That was 2 years of hearings and 6 to 8 years of regulatory processes at the federal level and actual construction. It's a $1.6 billion project. It might wind up costing consumers a little more or might wind up costing a little less. You don't know because you don't know where fossil fuel prices are going to go over the 25-year life of the project. But it's $1 billion worth of health benefit. So you can justify the project almost just in the health benefit because somewhere power plants have to turn off. Mm-hmm. You're not sure which ones, and that's sort of market determined and stuff. But so it's 3 months. To answer your question, it's 3 months or 2 years or 8 to 10 years, depending on
scale.
Whether you want to run your own house or whether you want to run 17% of the state of Delaware.
Right. So when just to so I can use numbers that are easy. If somebody installs a megawatt,
yep,
wind tower, the amount of time though that thing is ideal is it produces a megawatt 24 hours a day, 365 days a year. But in reality, sometimes the winds are blowing not enough, sometimes too strongly. So what's the actual? I don't know the correct term for it, but
capacity factor.
The capacity factor is what for wind?
On land wind, 30%, something like that. Mm-hmm. In the ocean, 40%.
40%. So when you said this supplies X percent of the total electricity for the state, does that include the capacity factor?
Yes.
Okay.
Right. People will sometimes report the capacity,
mm-hmm.
And that's really dishonest. So to take your 1 megawatt example. That's a 1 megawatt machine. If you look at the nameplate rating, somewhere
yep.
it's stamped, 1 megawatt. But if in our coastal site, for example, we're getting roughly 0.3, of that, so 300 kilowatts. That's our average output. Sometimes we're running at 1 megawatt. It's actually a 2 megawatt machine, but
mm-hmm.
To take your 1 megawatt example, sometimes we're running at 1 megawatt. Sometimes it's 0. Often it's in between.
Right. Right. So let's now scale this up and say we wanted to run the East Coast
yep.
on electricity from wind, from say offshore facilities, because that sounds like we have a better capacity factor there and
mm-hmm.
probably fewer siting issues.
Yep.
A variety of things might make that work. So in your opinion, talk to me about what would the process look like? How long would that take under say normal circumstances, which is the ones you've just described? So we have all the regulatory bodies and these things go through normal things and we have to find financing. Versus what could we do if we said this is an emergency? Sort of there's a federal the equivalent of martial law declared on this, and we can just go forward and sweep aside eminent domain considerations, all sorts of things. So I'm trying to put a box around this and say what's likely on one end and what's possible on the other end.
That is such a great question, and you asked for my opinion. Actually, I can do better than that. We've done extensive analysis on this with 4 or 5 scientists working on it, and have peer-reviewed publications out that address that question. So, first of all, we studied Cape Hatteras to Cape Cod. So that's the sort of northeast and mid-Atlantic. It's a large, shallow continental shelf. It's relatively windy. So the power demand of that entire sector, all those coastal states, is 73 gigawatts. A gigawatt is 1,000 megawatts, so it's a very large number. Whole U.S. is around 400 gigawatts. So average power is 73 gigawatts. That resource, if we just put turbines in the shallow waters, exclude shipping lanes, bird flyways, all that stuff, is 330 gigawatts. That's the average output, not the capacity. So we can easily run the entire East Coast electricity. So we started saying, well, gee, we got a lot more power than we need here. What do we do with it? Well, we can electrify the vehicle fleet. That's another about 30, I forget the exact number. So we're up to 100, we got 300. So, okay, what else do we do, So we can do, because the wind blows more in the winter, everybody says, oh, that's a mismatch. Well, actually, we use more energy in the winter. It's just liquid fuels, stuff that you're familiar with. So that's another, forget the exact number, something like 50 gigawatts. So in other words, you can run all electricity, all vehicles, and all building heat for the Northeast and Mid-Atlantic, and you still have only used 2/3 of the offshore wind resource. Now your question is, how fast can we do that? So we can calculate how many turbines and so forth, and the question is, at what rate, of course, so you can kind of draw out plausible commercial scenarios where you've built that out completely in 50 years. But that was not your question. Your question was, what can we do under emergency circumstances? So how do you figure what's an emergency circumstance? Well, World War II. Okay, so how did we do in World War II? What did we do in World War II? Well, one thing we did in World War II is built these long tubular metal structures with propellers on them, right?
Yep.
So it's not so different from a wind turbine, all the aircraft that were built. So what would happen if we built wind turbines for the Northeast at the pace that we built aircraft in World War II? Just counting aircraft versus counting wind turbines. It's not quite fair because there's more steel in a wind turbine, but so forth. It's approximate. You do it in 4 years. So you can take out 65% of the carbon from the Northeast in 4 years under the circumstances that you just described.
So at
martial law,
at the same pace. So we say this is how many planes we put through our factory system at that time when we wanted to, and if at that same pace it would take 4 years to build this thing out. You're saying?
Yeah, it's kind of crazy, but that's what we did. Now there's some downsides. You couldn't buy a Chevy, couldn't buy a washing machine. All the steel was going into that.
Yep.
And in fact, they were auto factories. Willow Run in Michigan, for example, was turned from producing automobiles into producing aircraft.
Okay, this is fantastic. So let me see if you've gone this far with it, because you just mentioned the steel. There might not be enough steel.
Yeah.
So within a turbine, its whole assembly, are there any elements or substances that would be a limiting factor in this? I mean, there has to be a capacity constraint somewhere, right? The factories, how many factory floors do we have? But secondarily are the resources themselves, the steel. I don't know what, it's probably copper windings up top, but there's probably some sort of a magnet structure in there which might have rare earths components.
Today's machines mostly don't have magnets, There's a movement to permanent magnet machines, but that's not happened completely yet.
Okay, so within the machine designs that we could domestically produce, do you see any capacity
That's something we haven't analyzed, the materials and kind of how you do a really large ramp up like you're talking about. Because usually I talk about that sort of ramp up, people say, wow, you could really do that quickly, but of course that'll never happen,
Yep.
So we haven't gotten to the second step of, how do you have enough materials and all that. We're working at the intermediate level of how do you get the policies to start moving at a commercial rate, sort of commercial speed, rather than how do you get the emergency order signed, which would be appropriate in terms of the climate science and ocean acidification. I mean, if the population kind of understood what the scientists understand, we would be doing just what you described, and we wouldn't need martial law. We would just mobilize,
right.
And we'd buy less of some consumer products, and temporarily we'd pay more for electricity. In the long run, this is going to be less expensive electricity.
Right. Yeah, I was only going to declare martial law on the regulatory structure.
Oh, yeah, okay, good.
Not actual martial law.
That actually you can get a broad consensus for.
I think a lot of people would jump up and cheer for that one. A fellow I followed for a while and had the pleasure of meeting, he passed away last year, is a guy named Matt Simmons, and he had an idea going that was in play at the time of his death, which was up in Maine. He wanted to use wind power offshore, but he wanted to use the electricity to then convert seawater into ammonia, in essence, right? So there's a structure there where they're harvesting the hydrogen from the water, and then they're recombining it with nitrogen from the atmosphere, a very energy-intensive process. But if you have, as it sounds like, you can get more energy than you need in certain circumstances, what we're really facing with peak oil is a liquid fuels emergency. Yes. And so this sounded like an interesting idea to me because it's a bridge between saying, well, we have technology in hand where we know how to create a lot of electrons. We look like we're facing a pretty significant shortfall in liquid fuels, and the gap between there is pretty large because in order to use electricity to transport things, it's very difficult. For instance, nobody's figured out how to run cargo airplanes with batteries in them on electric motors of some kind. Right. Even large trucks, anything that's hauling a lot of weight, very difficult. Small, light carbon fiber cars, easier. So have you heard about that idea, or has that been...
I think it's a great idea. I mean, I haven't studied the ammonia cycle enough to really comment, analytically on it. But I know basically you've got just what you said. You put electricity in, and you got a liquid fuel out. So that sounds great, and it's obviously it's closed loop, or it's a sustainable process. And that, of course, is another way of dealing with the problem of too much wind power. Because really, I mean, people always think, how do we fill in the gaps when the wind, what do you do when the wind's not blowing? That's really only maybe a third of the problem, actually. The bigger problem is, it is a problem, but the bigger problem is how do you deal with too much without just letting the electricity go away, feathering the blades and letting your investment not take advantage of that. So production of ammonia, for example, I mean, anything where the capital investment in the production equipment is such that you can afford to only run it, say, 25% of the time. Anything like that is great, and then you're creating a liquid fuel, great for transportation, and of course ammonia can be converted into other chemicals. But I just haven't studied the ammonia cycle enough to really comment on it intelligently.
Well, ammonia could also serve as fertilizer. It's a pretty interesting thing. The difference is that gasoline you can kind of trust the average citizen to go out and before their morning coffee and put it in their tank. Ammonia is a very different substance. It's gasifies easily, and it's highly toxic in a very corrosive way if it gets into the atmosphere. So there's a bunch of issues there we'd have to solve around that. One of the points I like to make though is that these are great ideas, but we don't have that cycle running yet. We don't have a single example of electricity going into ammonia, going into a fuel station of some kind, going into vehicles of some sort. There's a lot of work there still to prove feasibility of it, test it out, and start to get it ramped up into production.
Ammonia is a widely used industrial chemical, but you're saying there's not really any use of it as a fuel for light vehicles or heavy vehicles.
Right. I mean, you can't just put it in the tank. There's a whole reconfiguring that has to happen to the engine, and so they'd have to be built for ammonia. There's the issue of the seals. There's the issue of the compression ratios. All sorts of. It's just a different substance, but it works potentially.
And I guess it could also be used as energy storage, essentially, that then gets turned into electricity later. So the nice thing about that is it is a liquid fuel, so you've got high density, you can pour it into vehicles and so forth.
Yep. So that's an idea as well. So it sounds like wind has a really excellent potential then to meet a couple of needs. Have you studied solar?
Not
as much?
I mean, it's just right now, the resource isn't as large in terms of what's practical to put out there, because if you assume you're putting on rooftops, which the structure's already been built, the energy connection's already there, you're not having to build a lot of infrastructure, you don't have to run a power line out. So in the east, southeast, where we are now, in the northeast, in the northern parts of the country, that you really have to do that sort of thing, I think, to make it economic. And even so, it's quite expensive, 25, 30 cents a kilowatt hour compared to wind at around 10. And then in the southwest, you've got solar concentrating power, various technologies there that look very promising. And back to the storage question, when you're heating something up in a solar concentrating system, then you've inherently got storage. because you're using the sun to heat something, and heat is really easy to store and really cheap to store locally in one place. So then you generate electricity when you need it. So there's various ways of doing that depending on different fluids, where you've got the storage inherent in the power production device. So in the Southwest, I've looked a bit at the range of solar technologies there. But I've looked in the most detail at wind because it's a really large resource and relatively cheap.
Now hold on, I have a toaster, so I'm almost positive you can use electricity to heat stuff up.
Right.
Is that a possible storage solution that we haven't covered yet? Take the excess electricity and be dumping it into some thermal storage system?
Yes, and there's two ways to do that. One is the one I mentioned, where you've got a power plant of some kind. Mm-hmm. You're heating stuff up, and then as a separate step, you're generating electricity. So you just make your stuff that you're heating bigger. It's really cheap, you know. Mm-hmm. So you separate the heating of the material from sunlight, which occurs only during the middle of the day, from the generation of electricity, which can occur 24 hours. So that's one way to store it. The other way to store it is like your toaster in your house, or maybe a better example is your home heater. You're taking electricity, as you said, creating heat, and then you're using that heat to heat the house. Well, that's another really cheap way to store energy, but you're not going to get electricity back there because it's expensive to convert heat into electricity. Mm-hmm. And somebody else is doing that back at the power plant.
Right.
So in your home, though, you're going to need heat, you know, and you probably know about how much heat you're going to use tomorrow, or some smart control knows that. Mm-hmm. And so it says, midnight, hey, electricity's cheap right now, or the wind's blowing really hard right now. There's too much, more than we need. We're going to heat up these ceramic bricks to 1,000 degrees, say. And that's a cheap way to store heat in your home. And then tomorrow, maybe electricity's expensive, or maybe the wind's not blowing. But who cares? We got this really hot mass of bricks in the basement. Now you just run a very low energy fan, low power fan, over the bricks and heat your house. You never know the difference. The furnace is working. You don't have to know that you used electricity last night at 1 a.m. and you're getting the heat today at 2 in the afternoon. So that's an end-use storage technology that's smart about the grid and when there's excess or cheap electricity.
Great. So you've just used the term smart and grid, two terms right next to each other. For the people who, a lot of people have heard about it, I think. The term is certainly out there. What is a smart grid? And are there genius grids? Are we waiting for like an Einstein grid before we get started? Or like where can we get with a semi-smart grid? I mean, what is a smart grid?
Oh boy, I don't think anybody knows the answer to that question.
Okay, that's why it's so hard to define.
I was talking about a smart furnace on the grid, and I did get the words close to each other, but that was a mistake. It refers to at least two really different things. One is literally a smart grid. That is, you go through your neighborhood, you look up, there's poles up there, there's 3 wires at the top, there's 1 wire lower down, there's these cans on every third pole or so. That's your neighborhood electric grid. That's incredibly dumb. When you're in your house, there's an ice storm or something, power goes out, and then sometime later you see guys in these bucket trucks, you're really glad you don't have that job, and they're up there, fixing the wires. You know how they knew the lights were out?
So I called them?
Yeah. Or one of your neighbors called. They have no way to know that the power line's down and there's, 50 houses with no electricity. So that's a dumb grid. It's what we inherited from the work of Edison and Westinghouse and those folks. And it's really hasn't changed much since 1930 or so. And that's okay. It works and all that. But we've got, I got a computer in my pocket now that's called a telephone. And apparently it's got more computing power than the entire moon launch did from one of the speakers the other night. So why don't we get some of that out on the electric grid? So that's the smart grid, where the grid itself is smart. There's sensors. It knows when things are overheating. It knows when things are overloaded. This information goes back up to headquarters. But then what's smart at your home, what the smart grid at your home has mostly meant so far is automated meter reading, which just means they can pick up how much you're using each month without having to pay somebody to go out and look at the house. But the potential of that is that it would then also be linked to appliances in your house, and things would turn off at peak times of day and so forth, the kind of thing I was just talking about. So that's the vision, and kind of building an infrastructure for that. It's a very large ticket. It's a lot of money to change over all of that infrastructure, just looking at the house meter and things inside the house. So the areas that we've been working in, we've been trying to think of doing it with a device that's smart, that doesn't necessarily need a whole smart grid. So the furnace is one that I talked about, drawing electricity when there's excess electricity and providing heat when it's needed in the house. Okay, you could do that with a few controls and somehow linking to the grid to say, do you have excess now or not enough? That's just plugging into your internet router that you probably already got in your house anyway. And if you don't, it's a cheap ad. It's not changing out the whole electrical infrastructure. And the part of that we've been working on very similarly is using electric cars as storage. We think electric cars are going to come in pretty quickly. And at 2-3% of the vehicle fleet, electric cars become a very significant resource for the electric system. And I said resource rather than load. They're also a load, but they can be a resource if you design the car so that they either charge when there's excess electricity rather than when you first plug them in, or if you can, the next step is design them so they discharge and actually provide power onto the grid, the so-called vehicle-to-grid power, which we've been working on since 1996.
Oh, that's a fascinating idea. So we could store heat in a decentralized fashion in every house. We could store the cars themselves wherever they happen to be, whether they're at work or at home, depending on their loads. Of course, there's some sensor that has to say, where's this battery in its charge cycle?
Right.
Does it have extra? Do we need some?
Right.
So there's a whole lot of communication that has to go on there. I hear massive opportunity in there for a lot of companies, a lot of inventors, investors. This is definitely sounds like an incredible direction to go.
Yeah, and there's a bunch of people working in this space. We have pioneered it at the University of Delaware. I hold 5 patents in this area. We've licensed those to 2 companies so far, and we're in negotiations with a couple of others. So there will be a lot of commercial activity, and we hope it'll move very quickly.
Without, if there's any conflicts of interest, of course, don't answer. But do you see any companies that are leading in this space that you would consider to be? It sounds like the Wild West in essence, because this is brand new territory, right? So who's out there? Who's doing good work?
Well, we're in discussions with a lot of parties, but the ones that we already have publicly described are AC propulsion is a drivetrain for cars. So if you're a car manufacturer, you can put their drivetrain in or license their technology and do your own version of it, and that has this high power two-way flow of electricity. So I've got a university owns 3 cars that have this drivetrain in them, and when I've got it plugged in at my house and I tell it to go full power reverse flow, I literally am running my whole block from that car.
Really?
It's 20 kilowatts. Average house is about 1.5 kilowatts load.
20 kilowatts?
Yeah.
Does your plug melt?
Well, I paid $600 for the plug.
Yep.
Yeah.
You need a good plug
with the standard electrical installation, past inspection and all that stuff.
Yeah.
The transformer that goes to my house can handle I think it's 35 kilowatts. So we're well under the demand. Of course, they're normally thinking of it flowing to the house. So if my neighbors are using some, I actually can push more than the limit of the transformer out, because some of it's going to the neighbor and then others is going out. But yeah, everything is rated properly. There were no electrical upgrades needed other than the plug from our circuit breaker box to where the car is. So we've designed all this within the constraints of the typical electrical system.
And this AC power, is that what you called it?
Yeah. AC propulsion makes the
drivetrain. So this drivetrain, what's that available in right now?
There's a sort of custom-made vehicle called the E-Box, which is made by Autoport, which is a company that does remanufacturing of vehicles. So they'll take a vehicle and make it into a delivery truck with just the right brackets and ladder holders. Or they now are taking gasoline vehicles and turning them into electrical vehicles with this drivetrain in them. It's all hand assembled, so it's relatively expensive. The Tesla has the ability to do this reverse flow, but they're not using it right now because they want to understand better the battery impact. So obviously there is some battery wear if you're doing additional cycles.
Right.
And let's see what other companies. There's a company called Nuvi, which is just newly started up. They're working in about 5 countries outside of the United States. They have a license to use the technology we've developed outside the U.S. So they're targeting countries that they think are particularly good prospects for this as early adopters. So those are the 3 companies that kind of are already moving in this space.
Right. So they still all sound like this sounds like one of the next great waves. This is how all technology booms start. If you went back to the mid '90s, you would hear these same sorts of stories about technology companies, right, in the internet space. And not suggesting that we're headed for a crash or anything like that, but this is it. We don't have. It doesn't sound like we've got the equivalent of a GE just like really dominating the space. It sounds like there's a lot of inventiveness, innovation, entrepreneurial spirit. That's all bubbling up and going along. Is the government supporting that?
Yes, but just to the statement you made, I agree with, and part of the university's philosophy is that we license to anybody, So, some things make sense to have exclusive air over an area, over a certain territory. But for example, cars, we don't want to license just one car manufacturer. We want anybody to be able to license it. So that's very important. Has the government supported it? Yeah. There's been first state of Delaware, which. We're a little Delaware University, so we got the state to support us before the big guys would. And so they started out supporting enough to get us going with one car we could actually experiment with, and the power electronics to make that work, and to hire people and stuff like that. And then since then we have been funded by Google.org, by Pepco Holdings, which is a large power distribution company in the Washington, Maryland, Delaware area, and by the U.S. Department of Energy Electricity Reliability Division. So that's a big chunk. The DOE funding, which is we've just finished spending out. It's kind of gotten us to the point where we actually have a product to roll out. So those are all important sources of funding.
Good. Oh, excellent. I see we're coming up on the end of our time here. So, is there any last words that you want to sort of throw into something we forgot to cover here?
Well, one thing you and I were talking about yesterday that we didn't cover that much is peak oil. If we're going to hit peak oil, what are we going to do about it? And one answer is tar sands. Don't worry about the environment or the cost or how much energy you have to put in to get the oil out. But at all costs, preserve our current technology for light vehicles. And I think a better answer to that is electricity as a fuel for light vehicles. As you mentioned, it's not suitable right now for aviation, long-distance trucking, and so forth. But the light vehicle fleet, that is cars and light trucks, are most of the petroleum. And so if we can electrify half, 2/3, 3/4 of that fleet, it's cheaper. It's the equivalent of 80 cents a gallon gas, something like that. They're more fun to drive. They're going to be a lot faster. They're going to be a lot more peppy than gasoline, because you get full torque from 0 RPM. So the electric vehicles really take off. Which is why the Tesla early model is a sports car, 0 to 60 in 3.7 seconds, and all
amazing.
That. There's now a kind of motorcycle-derived 2-seater, which is like a speed demon vehicle, which does the same 0 to 60 in about 4 seconds, and then does 60 to 120 in 3.5 seconds. If you can imagine that.
Yeah, don't tell my son about that.
I think electric drive is going to just be seen as a really superior drive, a way to drive a car.
Well, and I was really taken in. There's a documentary called "Who Killed the Electric Car."
Yep.
And the most capturing moment in that thing for me was when the mechanic came out and he had two dollies and he said, "This is the normal stuff we just duty cycle have to replace in a gasoline engine or diesel engine. You know, there's filters, air filters, there's oily stuff, you know, there's just rings, spark plugs, there's all kinds of stuff." And he said, "This is on the other trolley, which was all clean and had no grease on it." He said, "This is what we have to replace on an electric motor." He had some bushings or something, you know, that was it.
And a pair of windshield wiper blades.
Yeah, it was just, that was a really, I mean, I was just thinking at that moment, it's like, wow, this is also, it's clean is more than just something you put air quotes around and say, oh, this is clean technology. Mm-hmm. No, it is physically cleaner.
Yep.
And with far fewer parts to be replaced because, anything that's moving needs to be replaced. Fewer moving parts, less to replace in the electric side.
And much lower temperatures. You're not dealing with combustion, all the byproducts of that.
So for people who live in the Northeast like me, do we have to put a little wood stove in our car, though? Because, that's one of the great things about combustion engines. You get the heat for the winter,
Right.
So
that's right. Yep. You have to either have that is a solution. You can put liquid-fueled heaters in. My old Corvair, 1962 Corvair, had a gasoline heater, because they didn't know how to get the air-cooled engine to heat the interior space, or didn't want to, or whatever.
All right, so this has already been solved.
Yeah, right. But it's a disadvantage in a sense. You have to design your own heating system. You don't get 85% of your gasoline going up as heat. Mm-hmm. So you got so much to spare, you don't know what to do with it. The car gets too hot. The other thing you do is while you're still plugged in, our system either it gets told or learns when you're likely to drive. So if the car knows when you're next going to drive within a certain level of probability, it can preheat the car while it's still plugged in.
That's a great idea.
So you use grid power to heat the inside, and then a much smaller amount of power to keep it warm while you're driving.
I hadn't thought of that. That's a great idea. Okay, I can see that. So I really want to thank you for your time. This has been a fascinating, illuminating conversation for me. I hope everybody else finds it that way.
Fun to talk. Yeah. Thanks for your great questions and comments.
You're welcome. The pleasure's been mine.
Yeah.
This concludes this podcast by Chris Martenson. To gain further insight into where things stand today and what might happen tomorrow, please visit chrismartenson.com. That's ChrisMartenson.com. Please join Chris Martenson next time to continue your journey toward awareness, understanding, and action.